On July 1, 2025, telescopes at the Asteroid Terrestrial Impact Last Alert System in Chile captured something extraordinary moving through the constellation Sagittarius. The object appeared unremarkable at first, just another faint smudge among thousands tracked nightly. But within hours, astronomers realized they were witnessing something profoundly rare. The visitor carried a velocity too high for our sun's gravity to explain, a trajectory bent into a hyperbola that would carry it back to interstellar space. Humanity had found its third confirmed messenger from another star system, and this one would prove more revealing than either of its predecessors. When outsiders arrive. Our solar system formed 4.6 billion years ago from a collapsing cloud of gas and dust. Every planet, every moon, every asteroid and comet that circles our sun shares this common heritage, built from the same primordial materials in the same cosmic nursery. But interstellar objects come from elsewhere entirely. They were forged in the planetary systems of distant stars, possibly billions of years before our Earth existed. They traveled for eons through the frozen darkness between stars before chance aligned their paths with our solar neighborhood. The first of these visitors arrived in October 2017, spotted by the Pan-STARRS telescope in Hawaii as it was already racing away from the sun. Astronomers named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The object puzzled scientists immediately. Its extreme elongation suggested a cigar or pancake shape between 100 and 400 meters long, unlike any asteroid or comet previously observed. More troubling, Oumuamua accelerated slightly as it departed the solar system, behavior typical of comets venting gas, yet it showed no visible coma or tail despite intensive observation. Theories proliferated to explain these contradictions. Some suggested Oumuamua might be a shard of nitrogen ice from a Pluto-like world, gradually ablating in the sun's heat. Others proposed it consisted of molecular hydrogen trapped in water ice, which would sublimate invisibly while providing the observed thrust. One Harvard astronomer, Avi Loeb, controversially suggested it might represent alien technology, a light sail or probe from an extraterrestrial civilization. By the time astronomers definitively determined its nature, Oumuamua had already passed Neptune's orbit, forever beyond detailed study. The second visitor arrived in August 2019. Amateur astronomer Gennady Borisov, observing from Crimea with a homemade telescope, spotted an object moving unusually through the pre-dawn sky. Within weeks, the International Astronomical Union designated it 2I Borisov, confirming its interstellar origins through its hyperbolic trajectory. Unlike Oumuamua, Borisov behaved exactly like comets from our own solar system. It displayed a prominent dust coma and tail, its nucleus measuring roughly 1 kilometer across. Spectroscopic observations revealed unexpectedly high concentrations of carbon monoxide relative to water, suggesting formation in an extremely cold environment far from its parent star. Polarimetric studies found that Borisov's dust properties matched those of comet Hale-Bopp, one of the most pristine comets ever observed from our solar system. This similarity suggested Borisov had experienced minimal processing since its formation, preserving materials from the planet-building era of its home star system. The comet passed through our inner solar system at 110,000 miles per hour, close enough for detailed study, yet never approaching Earth within 300 million kilometers. By late 2020, as it faded beyond detection range, astronomers had gathered unprecedented data about interstellar material forged around another sun. The third messenger. When 3I Atlas appeared in July 2025, it immediately distinguished itself from its predecessors. The object measured between 1.4 and 5.6 kilometers across, significantly larger than either Oumuamua or Borisov. Its trajectory carried an orbital eccentricity of 6.139, the highest ever recorded for an interstellar object, more than 5 times Oumuamua's value and nearly twice Borisov's. This extreme eccentricity meant 3I Atlas traveled through our solar system in an almost straight line, rather than the curved path typical of bound objects. The comet approached from the direction of Sagittarius, near the galactic plane where stars pack most densely. This region creates a challenging observational environment, with the comet's faint signal easily lost against the bright background of the Milky Way's core. Amateur astronomer Sam Dean later noted that 3I Atlas likely went undetected for weeks because it was crossing in front of the galactic center's dense star fields. Prediscovery observations eventually extended back to mid-May 2025, revealing the comet had been within detection range for 6 weeks before anyone noticed. Activity appeared early. NASA's test satellite detected outgassing when 3I Atlas was still 955 million kilometers from the Sun, farther out than Jupiter's orbit. Most solar system comets remain dormant at such distances; their ice is too cold to sublimate significantly. That 3I Atlas activated so early suggested either exceptional volatility in its composition or an internal heat source beyond simple solar heating. As it closed on the Sun throughout summer 2025, the comet brightened rapidly, eventually becoming visible through amateur telescopes despite its considerable distance from Earth. A comet that defies expectations. The surprises intensified as observations accumulated. In early July, multiple telescopes confirmed cometary activity, observing a diffuse coma extending thousands of kilometers from the nucleus. The coma displayed a reddish coloration characteristic of dust-laden gas, similar to Borisov but noticeably redder than typical solar system comets. Throughout July, this red tint deepened measurably, indicating either changing surface composition or evolving dust properties as sublimation exposed fresh material. But the most unexpected feature appeared in August. Instead of the conventional tail pointing away from the Sun, 3I Atlas developed what astronomers call an anti-tail, a structure that appeared to point back toward the Sun itself. Anti-tails are rare but not unprecedented. They occur when dust particles ejected from a comet's nucleus follow curved paths through space, and Earth's viewing geometry creates the illusion of a sun-facing feature. What made the 3I Atlas's anti-tail exceptional was its prominence and the structures visible within it. Observers using the 2-meter twin telescope at Spain's Teide Observatory conducted an intensive 37-night campaign between early July and early September. Their images revealed narrow jets embedded within the antitail, structures that maintained an almost constant position angle relative to the comet's motion. Precise measurements of these jets at a projected distance of 6,000 kilometers from the nucleus showed something remarkable. The jets wobbled, their orientation shifting in a regular periodic pattern with a cycle time of roughly 7.74 hours. This wobble represents the first periodic jet angle modulation ever detected in an interstellar object. The behavior implies that gas and dust are venting from localized active regions on the nucleus surface, likely near one of the rotational poles. As the nucleus spins, these active patches rotate into and out of sunlight, causing the visible jets to precess around the rotation axis like a wobbling top. If this interpretation is correct, the 7.74-hour wobble period translates to a nucleus rotation period of approximately 15.5 hours, assuming a single dominant active spot near a pole. Perihelion and beyond. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the Sun at a distance of 1.36 astronomical units, roughly 203 million kilometers. This placed the comet between the orbits of Earth and Mars, close enough for solar heating to drive vigorous activity, yet far enough to ensure safety. The comet blazed through perihelion at 68 kilometers per second relative to the Sun, faster than any previous interstellar visitor. Multiple spacecraft turned their instruments toward the passing comet. ESA's Mars orbiters, ESA Mars Trace Gas Orbiter and Mars Express, captured images on October 3rd when 3I Atlas passed within 30 million kilometers of the red planet. The observations proved challenging because both spacecraft carry cameras designed to photograph Mars's bright surface from mere hundreds of kilometers away, not faint comets at vast distances. Nevertheless, the color and stereo surface imaging system aboard ESA Mars succeeded in resolving the comet's coma, visible as a fuzzy white dot against the star field. NASA's Lucy spacecraft, en route to Jupiter's Trojan asteroids, photographed 3I Atlas on September 16th from hundreds of millions of kilometers away. The Wide-Field Infrared Survey Explorer captured infrared observations. Even the Hubble Space Telescope, typically reserved for the most scientifically valuable targets, observed the interstellar visitor multiple times throughout its passage. These coordinated observations represented humanity's most comprehensive study of an interstellar object to date, far exceeding the data gathered for either Oumuamua or Borisov. On December 19, 2025, 3I Atlas made its closest approach to Earth, passing 268.9 million kilometers away, well over 1.7 astronomical units. The timing proved fortuitous. A new moon meant dark skies uncontaminated by moonlight, allowing ground-based telescopes maximum sensitivity during this critical observation window. Teams around the world captured detailed images and spectra, documenting the comet's properties as it raced outward toward the outer solar system and eventual escape to interstellar space. The December revelation. But 3I Atlas wasn't finished surprising astronomers. New Hubble observations on December 12th and December 27th revealed something unexpected. Instead of the single dominant jet observed in July, the comet now displayed two distinct jets pointing in opposite directions. One jet appeared bright and well-defined, oriented roughly toward the Sun, despite 3I Atlas now being post-perihelion and receding. The second jet, weaker but clearly visible, extended in the opposite direction from the far side of the nucleus. This double jet configuration defied simple explanations. Before perihelion, when the pole that hosted the dominant jet faced the Sun, that geometry made sense. Heat from solar radiation would drive vigorous sublimation on the sunward side while the night side remained cold and inert. But after perihelion, as 3I Atlas moved away from the Sun, the gravitational deflection of its trajectory was only 16 degrees. If the rotation axis remained fixed in space, the original sunward pole should now face away from the Sun, no longer receiving direct heating. Yet a strong sunward jet persisted, and a counterjet appeared from the opposite hemisphere. One possibility involves thermal lag. Heat absorbed during the close solar pass could conduct slowly through the nucleus interior, eventually warming regions that no longer face the Sun directly. This delayed heating might activate vents on the night side, producing the observed counterjet, while the day side continues venting from stored thermal energy. Alternatively, the nucleus might possess multiple active regions with different volatile compositions that respond to heating on different timescales. Analysis published by Harvard physicist Avi Loeb noted that the relative brightness of the two jets shifted between the December 12th and December 27th observations. This variability suggests either that the jets undergo precession at different rates due to the nucleus rotation, or that the source regions vary in output strength. Over time, the persistence of the sunward jet months after perihelion indicates either substantial thermal inertia within the nucleus or continued exposure of fresh, volatile-rich material as sublimation erodes the surface. What 3I Atlas reveals. The wealth of data gathered from 3I Atlas illuminates fundamental questions about interstellar objects and planetary formation beyond our solar system. Chemical analyses from multiple instruments confirm the comet contains water ice, carbon monoxide, carbon dioxide, methanol, and hydrogen cyanide. The James Webb Space Telescope detected unusually high concentrations of carbon dioxide and nickel in observations from early August. The abundance of carbon monoxide appears elevated compared to most solar system comets, but not as extreme as 2I Borisov, suggesting 3I Atlas formed in conditions intermediate between Borisov's formation environment and that of typical comets from our Oort cloud. The rotation period derived from jet wobble measurements, approximately 15.5 hours, falls within the range observed for solar system comets of comparable size. This consistency suggests that fundamental physical processes governing comet formation and evolution operate similarly across different stellar systems. The nucleus appears to be a loosely consolidated aggregate of ices and dust, held together primarily by gravity and frozen volatiles rather than strong mechanical bonding. This structure matches what scientists call a rubble pile, consistent with formation through gentle collisions and accretion in the outer reaches of a planetary system. Estimates of the comet's age suggest it could be extraordinarily ancient. Tracing 3I Atlas's trajectory backward indicates it arrived from either the Milky Way's thin disk or possibly the thick disk. If it originated from the thick disk, a population of older stars that formed when our galaxy was young, 3I Atlas could be more than 7 billion years old, predating our solar system by 3 billion years. This possibility makes it potentially the oldest comet ever observed, a frozen time capsule preserving materials from the era when the Milky Way was still assembling its structure. The comprehensive observations also definitively ruled out several exotic explanations that had circulated in speculation-prone corners of the Internet. The Breakthrough Listen project conducted radio observations with the 100-meter Green Bank telescope, the world's largest steerable radio dish, searching for any narrowband radio signals that might indicate artificial transmissions. No technosignatures were detected. Similar searches using the Allen Telescope Array, the Meerkat Array in South Africa, and the Parkes Observatory in Australia all found nothing beyond natural cometary emissions and human radio interference. The future of interstellar exploration. The discoveries enabled by 3I Atlas have energized proposals for dedicated interstellar object missions. Southwest Research Institute completed a study demonstrating that spacecraft flybys of interstellar comets are feasible with current technology. Their analysis showed that 3I Atlas itself could have been intercepted if a mission had launched in mid-2025, requiring Delta-V budgets comparable to missions NASA has already flown. The key challenge is detection. Interstellar objects must be spotted early in their inbound trajectories to allow sufficient time for mission planning and launch. The European Space Agency's Comet Interceptor mission, scheduled to launch in 2029, addresses this challenge through a novel approach. Rather than targeting a specific comet, Comet Interceptor will park itself at the Sun-Earth Lagrange point L2, roughly 1.5 million kilometers from Earth in the direction away from the Sun. There it will wait, potentially for years, until surveys detect a suitable target, either a dynamically new comet from the Oort cloud making its first pass through the inner solar system, or possibly an interstellar visitor. Like 3I Atlas, when a target appears, Comet Interceptor will depart its parking orbit and intercept the comet, splitting into 3 separate spacecraft shortly before encounter to obtain multi-point observations. One spacecraft, built by the Japan Aerospace Exploration Agency, will approach to within a few hundred kilometers of the nucleus. The other 2 will observe from greater distances, mapping the coma structure and measuring how the solar wind interacts with cometary gases. This 3-point observation strategy will provide unprecedented detail about a pristine object that has spent most of its existence in the frozen darkness of deep space. The Vera C. Rubin Observatory, which captured its first images in June 2025, promises to revolutionize interstellar object detection. Over the next decade, Rubin's legacy survey of space and time will repeatedly image the entire southern sky every few nights with a 3,200 megapixel camera, creating a time-lapse record of everything that moves or changes. Simulations suggest the survey should detect between 1 and 3 interstellar objects per year, possibly more. Each discovery will provide advance warning measured in months or years, rather than the scant weeks available for Oumuamua. The message in the ice. As 3I Atlas fades from view, growing dimmer with each passing week as it races outward past Mars's orbit toward the asteroid belt and beyond, the data it delivered continue revealing secrets. The comet will cross Jupiter's orbit in mid-2026, Saturn's orbit by 2028, and eventually exit the solar system entirely, returning to interstellar space from which it came. In several billion years, it might encounter another star system, repeating this cosmic journey in reverse, perhaps bringing trace materials from our sun to alien worlds that won't exist for eons yet. But its passage through our neighborhood has permanently expanded human understanding. 3I Atlas demonstrated that interstellar comets can be detected, tracked, and studied in detail using existing facilities. It showed that these objects largely behave according to the same physical principles governing comets from our own solar system, suggesting universal patterns in planetary formation, the unusual jets, the extended activity, the ancient possible age, All of these features teach us that while interstellar visitors share family resemblances with local comets, each carries unique characteristics shaped by formation conditions we can barely imagine. 3 interstellar objects have now visited our solar system during the era when humans possessed the technology to recognize them. Oumuamua, strange and enigmatic, defying easy classification. Borisov, remarkably pristine, behaving exactly as theory predicted. And now 3I Atlas, larger and more active than either predecessor, displaying behaviors both familiar and surprising. Each has taught us something different about the diversity of small bodies wandering between the stars. Millions more likely exist, undetected, passing through the outer reaches of the solar system, too faint and distant for our surveys to notice. With improving technology and dedicated observation programs, we will find more in the years ahead. Each discovery will add another data point, another piece in the puzzle of understanding how planetary systems form and evolve throughout the galaxy. And perhaps someday, spacecraft will actually visit one of these wanderers, touching material forged around another star, connecting humanity with the cosmos on a scale our ancestors could never have imagined. The dark between the stars is not empty. It teems with fragments of ancient planetary systems, rocks and ice carrying the chemical heritage of distant suns. They pass through our neighborhood constantly, mostly unseen, occasionally revealing themselves to those patient enough to watch and wonder. 3I Atlas is departing now, its brief time in our sunlight ending, but the questions it raised and the data it provided will occupy scientists for years to come. And somewhere in the darkness, the next messenger is already on its way. If you've found this exploration of interstellar visitors compelling, make sure to subscribe for more deep dives into the phenomena reshaping our understanding of the universe. We live in an era when the galaxy comes to us, one frozen wanderer at a time, and every encounter writes a new chapter in humanity's cosmic story.